Okay, so for this problem that's reviewing some stuff with springs and some system of objects, there's really kind of two ways to approach it. I'm going to do the problem kind of both ways. So you're going to see two different approaches to solving the same thing. Whichever one makes more sense to you is what you should try to make sure you're comfortable with doing. Both of them work. One of them's a little bit faster, but a little bit more involved in how to think about it. The other one's a little bit slower, but much more of just a process you can follow the steps on, so it's harder to screw up if you're feeling a bit confused. So anyway, so for part A, we've got this system of blocks connected with a spring, and we want to know the force the spring exerts on the smaller trailing block. So my first thought on seeing that is I should draw a free body diagram for everything that's involved, right? Blocks A and B. And this is what's going to lead to sort of the slower and formulaic approach. So I'm going to call that F, the pulling force, Fs for the spring, and right, we also have normal force and weight, but those will end up not really mattering because we don't have any friction. Right? So there's my free body diagrams. Now we can write Newton's laws for each thing. Right. And on block A, it's pretty easy. There's just a spring force. On block B, it's only a little bit tougher. We have a positive pull and then the spring force in the negative direction. And since we care about solving for the spring force, F sub s, we want to use this system of equations to eliminate the acceleration. So I'm going to solve for the acceleration here and substitute it in over there. Move the spring force to the other side and factor it out. And now we can solve pretty easily for the spring force. And if we plug those numbers in, right, the pulling force is 4 newtons, and block B is 8 kilograms, block A is 2, and we get that's 4/5 or 0.80 newtons. All right, and so that's our answer. So that's way number one. Draw a free body diagram for every object, write a Newton's laws equation for every object, and then solve this system, right, that system of equations. So option 2 is similar but a little bit different. So for option 2, we have to recognize sort of that there's this kind of thing, right? This is blocks A and B together, and they have a combined mass of 10 kilograms, and we're applying a force to that, right? The spring force exists, but as we drew in the previous free body diagram, it sort of is internal to our system and cancels out, right? We had one that was pointing in the positive direction, one in the negative. So the net force on our blocks is really just the pulling force. So we can write one Newton's law for this, which is that F equals m A plus B A. That's very easy to solve immediately for what A is, right? So that's 4 over 10 over 0.4 meters per second squared. And that must be the acceleration that both blocks have, because they move together. And now we can think about block B, or equivalently block A, but block B is the easier one. Block A by itself has that acceleration, and the only force that causes it to accelerate is the spring force. Keep the notation consistent. Use just Fs. And so we can write that the net force, which is the spring force, equals MAA, or 2 times 0.4, or as you once again get 0.8 meters per second squared. So you can see it's the same exact answer. This one is a bit more related to what we talked about in the energy chapter, when we talked about sort of internal forces and external forces. And so if you can kind of think of that concept of systems, you can do this way. As you saw, it was a lot faster. But But either way works. There's no real difference. So that's part A in this. So for part B, we want to calculate how far that spring is stretched. And so we know the force of the spring. And we also know the spring constant. And so we have an expression on the equation sheet that the spring force equals Kx, where x is how far it is stretched. So we rearrange, and we plug in, and we get that 0.010, that's kind of an ugly one, did it again. Right? That's how far it's stretched. That's part B. And again, this is just on your equation sheet, but recognizing that you need to use it and writing it down, that gets you 1 point right there. And then simply using whatever you got, no matter what number you got, whatever result you got for part A, put it there. If you can't solve part A, make up a number and put it there. And then you can correctly relate that spring force to the distance it stretches. And that would be the other point. Right? It's 2 lines of work, and you don't even need to get part A right to get the full credit there. So those kind of test-taking skills will definitely help you out. So part C, we changed things up a bit, right? So parts A and B were sort of the initial setup. Part C, we've changed the system. We're now pulling on block A instead of block B. We're pulling just as strong, but the opposite direction. And so part C is asking, is the magnitude greater, less, or the same? And this one, if you took this approach to thinking about it, part C is very, very, very fast. Because you immediately recognize that the net force is the same, the total mass is the same. So this equation still applies, I just have flipped the direction of the acceleration. I'm only asking about the magnitude. So if you did it that approach, you'd immediately conclude the acceleration is the same. And you justify it by saying something like net force, same, mass, same, so A, same. And it's important to note that however you want to phrase that again, it's important to explain exactly your reasoning process. You can't just kind of write one line, something like nothing changes about the system. That's not good enough. You have to reference sort of what equation, what you're using is Newton's laws, and so the things that matter are the net force, the mass, and the acceleration, how those relate. So that's option 1. If you did it as that sort of that faster way, then I think part C is really, really, really easy. This way, right, with this system of equations, the fastest way to do it is to actually just go the same process and just calculate that it is exactly the same, right? Draw the new free body diagrams for block A and B, and you'll find out that mathematically the acceleration is the exact same. And that would prove it too, right? You use Newton's laws to show it. So if you're more comfortable with the math, you can just do the math. It looks the exact same as part A. I've just changed which one I call block A and block B, essentially. Next is part D. I wonder if the spring stretches more, less, or the same. And this one, again, this one I think is actually faster if you did it in the first way I showed part A, the multiple free body diagrams in the system. But either way, I think that it's pretty clear. So the answer is that it has to be stretched more. So that's the result. And the reason is that in the initial picture, the spring is only pulling the 2 kilogram, right? So it only has to accelerate that much mass. And after, right, in the second picture, the spring is pulling the 8 kilogram mass. So because it has to apply the same acceleration, right, A must be same, right, we showed that in part C. Because the acceleration is the same, but the mass is bigger, the force must also be bigger, right? If the force is bigger, and the spring constant hasn't changed, which it didn't, then we have to conclude that X is also bigger, right? And so some justification along those kind of bullet-pointed things about what changed, what stayed the same, and how all those relate together is really what you want to do. And there are, the other way, right, is you could just simply calculate it again. If you took the approach of drawing the free body diagrams, you would get a value for the spring force, right? The spring force is a certain amount of newtons. You'd see that it's no longer 0.8 newtons. It's not the same as what you calculated in part A. And from that, you could then do, like, you could redo parts A and B in their entirety and answer part D that way, right, with the actual calculation. You would end up calculating that the spring extends 0.04 meters instead of 0.01, and that would also prove it, right, if you just simply do the math. Either approach is a good justify. All right, and finally, part E. So now we've got the thing moving at a constant speed, and we've stopped applying the force, and block A hits a wall. We want to calculate the maximum compression of the spring. And so both blocks are moving at the same speed because the spring is not stretching, and so we are going to conserve energy. Right? That's what this is really happening, is that the kinetic energy that we had is being converted into spring potential energy. So we say that energy is conserved, right? There's no friction, so we only have kinetic energy, that's what we have before. And after, we have spring potential energy, right? 1/2 kx squared, which is that maximum compression. And so if it was anything other than maximum compression, you still have some kinetic energy left over. But at maximum compression, remember, the blocks are instantly at rest. They're about to bounce back and go back the way they came, but at maximum compression, they're instantly at rest. And we use the total mass, right, because there's two things that are moving, blocks A and B both. So the 1/2s will cancel. And so we get, this is MA plus MB over K V squared equals X squared, or X equals V square root MA plus MB over K. And as I do this, I realize I made a mistake about the exact endpoints of when we consider the energy conservation statement. So this is actually not the total mass, and it's not the total mass because we assume that block A has hit the wall and stopped, and so only block B is moving, and that's what compresses the spring. So energy is conserved sort of in the block A has hit the wall and stopped, and block B is still moving. It's instantly, before the spring starts to compress at all, still moving at that initial 0.5 meters per second. But block A has already sort of lost its kinetic energy, and it's in elastic collision with the wall. So we can only conserve energy considering the motion of block B after it hits. So this is slightly different than what I wrote here. Right? And so you plug those in, and you'll get that X is 0.16 meters. And that's your final value.